So we're continuing our review. We went through the first exam last class period. So now the material for the second exam, we talked again about the wave method, which was pioneered by Schrodinger, and reminded that we separated the Schrodinger equation into the time-dependent and time-independent parts. And we worked with the time-independent part pretty much exclusively. But we can't forget that there is the time-dependent part, hence the test question where you had to include the time dependence portion. Right. So we had the stationary states and energy eigenstates. What condition led to having these stationary states with specific energy eigenstates?
What led to them?
Yeah. I didn't hear what you said, Indy, so I can't answer yay or nay.
I was just reading the PowerPoint. Stationary states and energy eigenstates.
Well, what's an example of where we got scattering states? If it's unconstrained, we have the scattering states. So for instance, you could have the situation of a potential energy spike, and it will scatter off of that spike, but it doesn't have specific energy values. It just has, continuous waves with all energies possible.
Okay.
Yes. Okay, just making sure we have that understood. When we talked about the neutron star, when we talk about a hydrogen atom, we have specific energy states. It's not confined in a specified hard-walled object. It's confined because you have a potential energy function that makes it so it's going to be preferentially close, not far. So confined isn't the same as in a box, but it's constrained to be in a certain location because potential energy function. And as a final thing for the waves, we of course have to have them normalized, which we've gone through a lot, and they have to be mutually orthogonal, your wave functions, which gives you the one combined relationship. It's 0 unless n is equal to m, and then it's 1. Okay, so that was review that we started for the second section, and that was on the test. And then we had the matrix method. So now we had the all new methods that we're working with using matrices rather than using differential equations. And we have one example where it had to be used, where there's no option but using matrices. What's that one example we had? Most recently, yesterday. What did you say?
I said the free particle, but you said we did it yesterday. So.
Yeah. Well, of course, you weren't there, but Indy was. Chris was.
Wait, what?
Doing our homework yesterday, we had an example of the case where you cannot do it with differential equations. You can only solve it using matrices.
I'm blanking on what we did yesterday.
Spin.
Is that dealing with the? Well, yeah, with the spin.
It's an intrinsic property. You can't come up with a wave equation for that.
Yeah.
And so the only way to deal with it is with matrices. I was looking at the homework that I've assigned in previous years, and I've assigned a whole lot more problems with matrices than we did in this class, like with the angular momentum, raising, lowering operators, making matrices for that and doing it with the matrix method. Because you can do your problems either way. But we generally did matrices only for the things that we could only do matrix with the spin things in this year. So with the matrix method, What is an operator?
You mean the where or
How do you represent an operator using linear algebra?
so you have your operator, and then you have the ket, right?
Well, an operator acts on something and then produces something else, right?
Equals the eigenvalue for the, yeah.
Okay, so this equation I wrote, that is your fundamental operator eigenstate relationship. And that could represent either a wave equation or a matrix equation, a linear algebra equation. So in a linear algebra equation, how do you represent your operator in linear algebra?
You mean like how do you represent it? Like how do you write it in nomenclature? Just
No, mathematically. What do you call the thing mathematically that represents an operator? I know you guys know this, but it's good that we're reviewing it because it'll help to make connections. It's a matrix.
Oh.
A matrix is an operator. So for instance, we've been working with 2x2 matrices for the most part because it's the easiest math. But we did one problem that was something like, okay, I don't know. I just made up numbers. So this could represent an operator.
that makes sense.
And then what do you use to represent an eigenstate?
So then your eigenvalue times your column vector.
Okay, the eigenstate is the vector.
Yeah, the column vector is the eigenvalue.
Oh, sorry, I thought you were talking about something.
The ket is a column vector.
Oh, yeah.
And the bra is a row vector. So I could, for instance, have state 1 is equal to 0, 0, well, traditionally we would put it like that, 1, 0, 0. And so if I write the bra for that, what would it be?
It'd be 1, 0, 0, but in a row.
Row vector.
Now let's go a step further. Let's say that ket 2 was equal to 0, 1i. Well, times 1 over square root 2 because it needs to be normalized. So what would bra state 2 be?
It would be 0, 1, negative I.
Right.
That's the 1 over square root 2.
Right. So we've got that complex conjugate aspect that we have to keep in mind when we're converting from the ket to the bra, or from the bra to the ket. Let's well, this may be the same as the problem we did in class, or it may not be, or in class in homework. Let's take this and find the eigenvalues and eigenvectors and unitary matrix to rotate everything. So let's find these three things from that matrix. So start me out. How do we start out?
Well, you're going to find your eigenvalues by taking the determinant of A minus the identity matrix lambda, which is 0, 3, 0, 3, 0, 0, 0. 1 minus lambda. Yeah, and minus lambda is 1.
And what does that equal?
I made that mistake. What?
And what does this
N
equal?
equal to 0.
All right. So then we have to do our multiplication.
Let's use the last column or bottom row.
Okay, so we use the last column. So it's going to be 1 minus lambda times
Lambda squared minus 9.
That was really a good choice because this is so easy. Of course, I mean, if we'd used the bottom row, it would have been similarly easy.
1 and plus minus.
So we have 3 values. So those are our eigenvalues. So we've got the eigenvalues. Now we need to find the eigenvectors. Go ahead, Chris. You said we do it a different way. Do it your way.
What?
Yesterday you were saying, well, you were saying that in your linear algebra you've been doing it a different way.
No, that's fine. How like all 3 classes have been doing eigenvalues. I guess it's a little bit different. So in linear algebra, I don't remember either. So starting with the first eigenvalue,
Uh-huh.
we're gonna plug it in.
They're just gonna plug in the lambda values for lambda in that matrix and multiply it by.
Which is different from what we would do because
Well,
normally we would take.
I'm thinking about
Yeah, same.
well, okay, let's be clear. What you're doing is the same thing, right? If you do this,
We're gonna take. Okay. Yeah, so it's
this is the way, oops. Well, it's not an oops, got to turn that off. This is the way I've been doing it. That's exactly the same as doing there is absolutely no difference in the two. You've just done the subtraction already in the second one. Yes, you subtracted lambda times ABC. And this is, of course, this is where we got that determinant has to be 0 if these are going to be independent equations, or not independent equations if you have, yeah. That was wrong statement. Let's not worry about what it should have been. But that's where we got the determinant of this has to be 0.
Right. So we're going to use lambda 1 or lambda equals 1 to find our first eigenvector.
Okay.
In which case we're going to have 3b equals a, 3a equals b, and c equals c.
All right. That makes life easy. There's only one consistent way to answer this. Doing a substitution. How can we make 9 equals 1? Or a equals 0? There's only 2 ways that can be true. And of course, 9 equals 1 can't be true. So a has to be 0, and that means b has to be 0. And what's c? Okay, I'm going to start by saying c is anything.
Choose one.
Choose one. Choose one because it does have to be normalized. right? So when we go through normalization, we'll find that C, the square root of, C squared is equal to 1 is what we'll find, which means that C could be, technically C could be e to the I phi, where phi is any value, as I talked about last class period. And we'll just stick with 1. So we have 0, 0, 1. No, don't choose C to be 0. That's not a good. I know you both did that on the test, but it's not a good choice. Yes, not the one we were aiming for.
You know how they always say choose C, C is the right answer? Well, in quantum mechanics, it's always trivial solution.
In differential equations, I wanted to put that anytime when he didn't say not the trivial solution. Okay, so what about when lambda is equal to 3?
Well, we're going to have 3b equals 3a. 3a equals 3b. And coincidentally, c equals c. Oh, 3c. Yes. 3c.
All right, what conclusions can you draw from this?
Say that A would be, so, and C has to equal 0. So I guess A and B could be anything as long as they're the same. So A would be 1, yes.
Yeah, you put the normalization constant out front, which at this point you're astute enough, I'm sure, to say, hey, when I normalize, 1 plus 1 is 2. And then if I square root, yeah. So, I mean, on the test, you should show, if you have to do that, show that's how you got there. Don't just say, look, I'm not an idiot. I know it's 1 over root 2 for its normalization constant. Actually show it.
Yeah. Okay.
And of course, you could have multiplied by any random phase.
So, question.
We choose one. Yeah.
If we did that on a test, or the final, for instance, and we know that it's 1 over square root 2, but in trying to show it's 1 over square root 2, we actually get something different. Can we just write 1 over square root 2 and not
you would still lose points, right? That's why I want you to show it, to show that you know how to do it. And if you show the right method and have a math error, it would be a very small loss. If you did the wrong method, it would be a bigger loss. Okay, so that was 3. And I don't know why I called that ket for 2 when that was ket for 3. Now let's do minus 3. So what do we get then?
So 3b equals negative 3a. And 3a is negative b, and c equals negative c. So a was negative b, and c still equals 0. So our vector is just 1, negative 1, 0 this time, or how you want to do it. 1. Negative 1.
Now, something that I want to do, what are the rules that these have to obey?
They have to be orthogonal in
Yeah, we already did the normalizing in our heads. Hey, we went 20 minutes. No complaints there, right?
Pretty good. Yeah.
So how do I check orthogonality?
So that's when you can multiply them together.
Yeah, so you're going to take.
Let's first do it in Dirac notation, then using linear algebra.
Okay. So you can do raw vector 3 1 times 10 to the negative 3. Yeah.
Okay, so there's the Dirac notation. Then how do I write it using the linear algebra notation?
So then it's the row vector, I guess 1, 1, 0 times its normalization constant. And then times the column vector, 1, negative 1, 0 times normalization constant.
I put the normalization constant so the two linear algebra things are next to each other. Okay, now that was only 2 minutes there. Yay, those are orthogonal. You know what? I'm going to skip the last one because anything, right, 0, 0, 1 and x, x, 0 is always orthogonal.
Yeah.
So, yeah, there's no point in doing it. You have a 0 in each thing you're multiplying. So we have part 1 and part 2 done. We've got the eigenvalues. We've got the eigenvectors. What's our unitary matrix that's going to diagonalize this?
Is that the, whenever we were talking about like the S, like inverse and like in the S and that stuff? Yeah, so, yeah. And so is it like the multiplication of the, or not the multiplication, but like all the eigenvectors added to like one vector or one matrix?
Yeah, you just stack them. And you have to actually put them in correctly. You got to put in your 1 over root 2's here. So there's my unitary matrix that's going to diagonalize it, according to me. And so for unitary matrices, life is good. Hermitian conjugate is the inverse. So the Hermitian conjugate of that is right. I just did the transpose and did the complex conjugate. There were no i's here, so it came out real simple.
Right.
Because we had chosen no i's. We could have put i's in all of these if we'd wanted to. So now let's check this out. Well, first, we should check that out to make sure that it's true. This is just a lot of writing. You know what? I've got copy and paste capabilities. They would even be better if I would catch everything in it. You can see I missed one of the zeros. Okay, so there's S inverse. Now, don't you wish you could do this on the test? I'm going to put the other one in the middle there. And now you guys have lots of experience with multiplication. 0 times 0 is 0.
20,000.
Oh, so close. 1 over root 2 times, and remember you're going, I know you guys are totally in linear algebra. Me doing this is almost insulting to you, but just making sure that we're all on the same page. So I have 0 plus 1/2 plus 1/2. You're both going to get A's in it, I'm sure. 0 plus 1/2 plus 1/2 is 1. Do I need to talk to your teacher to make sure you get A's?
There's a problem with my grade right now, and it doesn't have anything to do with my understanding of linear algebra. It just has, it has to do more so with my motivation to go to class.
Oh, that's a problem. Is Patty your teacher?
No, it's, Ron Johnson, Dr. Johnson.
Okay, I don't know him. Yeah, and Dr. Anderson, my bad. Over spring break, I was talking to Patty on the phone, so we were discussing you guys. Yeah.
Great.
Okay, so there's my first one. The second one, hey, look, 0 plus 1/2 minus 1/2, 0. Last one, 0 times 1 plus 0 times, 0. Middle row. That's going to be 0 plus 1/2 minus 1/2 is 0. And then 0 plus 1/2 plus 1/2 is 1. 0 times 0 times 0 is 0. And last one is, 0, 0, and Sure enough, it works out. Yay. Aren't you glad we don't have to find these things the hard way? I hate to admit this, but we had a math class where they had to do projects, and a student was showing the spectrum of, she was, instead of Hermitian matrices, it was real matrices that are symmetric under transform, which is just the special case of a real Hermitian matrix. And she was basically doing this work. For her eigenvectors, she got 0, 0, 0 for one of them. And so I raised my hand and said, you can't have the null vector as one of your eigenvectors. And after that, it all broke apart. I felt guilty that I, interrupted her train of thought, but her train was already off the track. So, okay, so now we've got a harder one to do. So don't be like that. Multiply the first matrix, first two matrices, then multiply that result by the other. So, you guys didn't learn any complicated way of doing it all at once, did you? As far as I know, that would just be a horrendous problem. So multiplying this, I've got the white pen. It never works out the way you want when you have the white pen.
You still have the white pen.
But I just changed it to black. You saw me change it to black and draw a line. I didn't do it. Okay, the next one. 0. Yeah, I went over it too. And the next one is and the last one. Part of the reason I'm doing this is because there's always the option that I could have had my S minus 1 and S reversed. And so I'm doing this to make sure that I didn't make a mistake. Hence, if I made the mistake, I've already set the table. It can happen. So already we see a problem, right? I did reverse them, because that was not one of our eigenvalues. Well.
That and your Fahrenheit It's not diagonal.
Yeah, it's not diagonalized either. Okay, so what does that mean? Boo. Yes. So it has to be flip those two positions. Now I'm looking at the time like, oh, didn't calculate this into the time.
What? Did you say that? What, did I say that out loud? Yeah.
See, that's why Chris is changing to a physics major. Wants to be just like Indy. Crud.
Words.
Okay, there. It's now written the other way. If it doesn't work out this way, then your teacher just done goof because we know that it works.
0, 1.
Did I make a mistake that you identified, or?
No, we were just talking.
We're talking about how we should have been able to tell which one was.
Oh, how's that?
No way.
I'm clearly missing something. How is it that you should have been able to determine? Because if there's a way that I didn't remember, that's good to know.
So I said that we should know about the things and the places that they shouldn't have been. And so, yeah.
I think end of the year stress reliever / anxiety is building.
Okay, here's our first good sign. 1,
You know, sweet.
and then the rest of them are zeros. And then we have 3 halves plus 3 halves. It's 3. Okay, the first one's 0 to 0, right? The next one, 3 over root 2 times 1 over root 2 is 3 halves. 3 over root 2 times 1 over root 2, 3 halves, 3 halves. And then the last one here, 3 halves minus 3 halves is 0. 0 minus 3 halves plus 3 halves is 0. Minus 3 halves minus 3 halves minus 3. Bueno! Yes, indeed. So, just fix that right off the bat and good to go.
Easy.
Yeah, just making sure I'd written it the way it's consistent now. Okay, so we found the unitary matrices that will diagonalize it so that now, if you had started with this, what would your eigenvectors be and your eigenvalues?
Well, your eigenvalue would be 1 to the negative.
Yeah, because you can read them on the diagonals, and your eigenvectors would be your eigenvectors would be 1, 0, 0, 0, 1, 0, and 0, 0, 1.
Okay.
Right? When you diagonalize it, then you know your eigenvectors instantly. That's the beauty of having it. Go ahead.
Question.
Yeah.
How are the eigenvectors 1, 0, 0, 0, 1, 0, 0, 0, negative 1? And we showed that they weren't that.
Well, the eigenvectors to this matrix is what we found. Then we diagonalized the matrix. So we made the operator So it still has the same eigenvalues, but is essentially rotated, right? It's a rotation process when you use that diagonalization. If you think about your vector space. And so now this has a different set of eigenstates that is still going to be complete, that can be a map from one to the other.
Okay.
And these eigenstates are going to be the 1, 0, 0, 0, 1, 0, and 0, 0, 1. And in fact, this same process can be used to diagonalize your eigenvectors. See, if you multiply, you put a vector in here, yeah, I think all you do, I should have paid attention to this, but I wasn't thinking about it beforehand. That should be diagonalized, then you're going to have just going through the same. Okay, I missed a few zeros this time. And so that was, which one was 1?
0, 0, 1, right?
Yeah, it was 0, 0, 1. Well, this one here is reasonably trivial. Yeah, you're right. You can't. I'm trying to think about. Okay, so I'm going to cross it out. That way you have record that I did it wrong. I know it's in the textbook. We got 10 minutes left.
Wait, go back to the diagonalized matrix. See, you got your first thing right there.
What?
1, 0, that first column is the multiplication you just got by multiplying the inverse of x times the vector.
Yes, but that's not what I'm trying to show.
Is that just
I was sure that here in the appendix, it showed. Where is it? I know it's here, but I don't see it here. I don't want to spend an inordinate amount of time on how you transform your vector, but it is an important thing because there is the same unitary matrix does transform your vector. It's just I apparently didn't remember how to do it correctly. Because, like you said, you can't multiply that. Yeah. Yeah. Well, I will look it up and add it to the. I'll add it to the notes later, so it'll magically appear. All right. Notice that wasn't one of the things I said to do because it wasn't one of the things I was prepared to do. Okay, so our operators have to be Hermitian. We talked about how to find the eigenvalues and eigenvectors from it. The way functions are vectors, the way functions live in Hilbert space. What does it mean to be a Hilbert space?
They are
It's a complete inner product space. That means the inner products give you real values, i.e., when you do your psi star psi, it's always going to be normalizable. And right, that's what it means is the inner product space. And it's complete, meaning that you can always describe any function as a linear combination of each of the eigenstates. Okay. And then we'll look at the test, and we won't do much of the test, which I know I was planning on spending a lot of time on the test. Explain what orthonormal means and why stationary states must form a complete orthonormal set. Well, we've just gone through that enough. We talked about orthonormal completely already. And Dirichlet's theorem, I said, will be useful. Dirichlet's theorem is basically taking Fourier and applying it to the Hilbert space, saying any function can be made as a linear combination of the other, of the eigenfunctions, which is what it means to be a complete space. There, all answered. Describe one of the two methods that was used for the quantum oscillator. So the quantum oscillator, that is, instead of the simple harmonic oscillator, you had the quantum state. With the ladder operators, we took the Hamiltonian, and being real tricky beasts, we created a new set of variables. And based on those variables, we created operators. And it turned out that those operators either raised or lowered the state, and that's how we called them ladder operators. So in this case, we learned what the operators did after we had made them, because we're always doing these problems that somebody else solved before us and taking their knowledge to make it easier to write down. And so then with the raising, lowering mechanism, we were able to find what the eigenstates are for the Hamiltonian, and we were able to then use the actual wave function equivalents for the raising, lowering operators to find what the actual eigenvectors were. For the analytical method, we went through and changed the variable to a simpler variable. And, okay, before I should have said, it was in the Hamiltonian that we rewrote it. We didn't make a new variable. I misspoke that. We rewrote the Hamiltonian in terms of these two new invented operators. Whereas the analytical method, we actually made a new variable and said, let's, instead of talking about X, let's talk about this thing. And then with this new variable, it was an easier problem, but still not easy. And then we took the long range solution, that is, if it's a big amplitude, and found the solution there. Then we took the small range amplitude, if it's a small displacement, and found the solution. Or actually, no. Sorry, I was thinking hydrogen atom. I was thinking ahead. We took the large amplitude solution, and then we said, now let's just say it's got to be an infinite polynomial will answer any function according to Fourier or Dirichlet. And so we put that in, and then we realized it had to terminate, and we got our solutions. Yeah, I went through that quick. List the two boundary conditions that a wave function must adhere to for boundaries that are not infinite. What are the two boundary conditions if it's not an infinite boundary?
So they have to be continuous, or psi has to be continuous along the boundaries, and the derivative of psi also has to be continuous.
What if it wasn't an infinite boundary? Or excuse me, what if it was an infinite boundary?
Well, it's all, how do you say it? The derivative isn't continuous.
And I'm not going to ask you on a test to do it. But basically, you integrate the Schrodinger equation up once to find the limit of d psi dx before the boundary to d psi dx after the boundary. And so you had a finite jump in the slope that you could actually calculate by integrating the Schrodinger equation with the actual potential energy function in there. What is a commutator? I didn't ask you to do it here. I just said, what is it?
It's like the difference in the difference in the change of order of the product of two operators.
Yeah. It is the difference in changing the order of the operators. I mean, if it was numbers, it never would have mattered. So it wasn't until we got here that we have this idea that, oh, I have to put this one first, then this one, or I get a different answer. And so it tells us what that is. It has a really important outcome that we didn't learn at this point, but we learned later. If the commutator is 0, then they must share eigenstates. And if they share eigenstates, then you have no uncertainty relation. You can know both of them at the same time. And so there's an important outcome there. If they commute, you can know them at the same time. So we can't know position and momentum at the same time because they don't commute. But we can know position and energy at the same time because those operators commute, if I remember right. Okay, define phase velocity and group velocity. I'm not going to test that on the final exam, so I'm just going to skip over that. 2 minutes. A system has potential energy described here. It was written wrong, so you had 2 choices on how to do it. But make sure that you can do the particle in the box problem and that you can do a finite well problem. Notice I acknowledge the inconsistency between the description and my table. My intent was different than what I wrote. And so you guys took different meanings from the problem, and that was perfectly fine. I graded based on how you interpreted it. So we had, sketch the potential energy, find the solutions in each region, apply boundary conditions for each one. Because they weren't infinite boundaries, it was just the 2 boundary conditions that are fairly easy. And when you apply those boundary conditions, when you apply the 2 boundary conditions, you should get your quantum condition. You should have quantized energies at that point. And then normalization gives you the final wave function. And did I have you normalize it? Yeah, the last step here was to combine the time dependent with the time independent solutions. And so you had the time dependent solution that is always this, if you can separate. And so then your total solution is just the combination of the 2. And so I put that in there because you have to remember, we're only working with the space part, but there is the time part. And then you had to find commutators because you'd had problems with those. Okay, class time is over. I'll see Indy on Friday. We'll have a party. I'll bring the root beer, you bring the pizza.
Will do. Share it to the cameras.
Yeah.